Good afternoon and welcome to another exciting edition of Gospel Live, Gospel's series of webinars on topics of interest to people across the technology industry. I'm Reuben Thompson. I'll be your host for this afternoon, where we'll be talking about consensus and agreement without bias. So I think we need to start off today by just looking at what we want to cover with this webinar, what we're doing today. So I think we've got three objectives. Now, the first of those is to understand what consensus actually means within the technology sphere. I mean, it's a phrase that we hear in other senses, but how does that differ when we're talking about technology? Secondly, I think we should look at how consensus is used in blockchain. This is a topic that's obviously pertinent to ourselves and also one that we've heard a lot of talk about in the last few months and over the last year or so. And thirdly, I think we should look at how gospel is unique in how we use consensus and the things we derive from that. Now, I'm going to be very clear, it's not going to be a sales pitch this afternoon, so I'm not trying to sell you anything. I'm sure my colleagues will be very happy to do that. So we're going to look at this as even-handedly as we can. If you have any questions, please do pose them either through the question and answer facility within the webinar interface you're looking at now, or if you're watching this as a recording, by all means, drop us an email to step.forward@gospel.tech. So let's kick off. So what is consensus? Now, in the simplest sense, consensus is agreement. Now, there are lots of places where consensus is important, and it kind of comes in two forms. One of those is agreement about what we should do, and the other one is agreement about what the state of the world is. What is the truth, which is something that I feel is very pertinent in today's world. So if we look at some examples of real-world consensus, it might be, which pub shall we go to tonight? We need to come to an agreement on that, and we need to decide where we're going to go. So consensus is required. We come to a shared decision. We might say, what route should we take to drive to Grantham today? Again, we need to agree, because otherwise we won't get there at the same time. And thirdly, from that second type of consensus I was talking about, the state of the world, what day is it today? If we can't agree what day it is today, many other decisions will be very hard to make. Now, in the computer world, there are a number of places where consensus is used to make things possible. Now, I've pulled out three examples here. Now, the first of those is database replication, something that I'm pretty sure that most people listening today will have had some experience of. Now, when you run one database, that's fine. When you run more than one server doing the same thing, it's quite possible for them to become out of synchronization or out of time with each other and to get different answers by asking different servers. Now, in a simple SQL sense, normally that is resolved by having one of the master servers and the others follow it, and you rely on something called eventual consistency, which is, in the end, you expect everybody to have the same version of the truth. If something is very, very important, you read it or write it to the master server. If it's less important, you go to one of the others. With some of the newer types of databases, things like React, Redis, some of these systems, Mongo even, that use more complicated methods of ensuring a consistent state of the world, more complicated things are done. So, for example, within Mongo, there is a facility whereby servers vote as to what the state of something is, and sometimes you need to break a deadlock in that by having something that just votes yes all the time. You then get things like fault-tolerant sensors. So if I need to monitor something very important, I don't know, is this submarine filling up full of water? Should we fire this nuclear missile? Something like that. Is it on fire? Then we might use multiple inputs of similar sensors that independently observe the event that we want to look at. And we look at a way of resolving any discrepancies between what they read. Again, this is consensus. So if we have two sensors that say something is on fire, then it's probably on fire. If one says it's on fire and two say it is not, then there's a good chance something's wrong with the sensor rather than with fire. Thirdly, blockchain uses consensus very extensively. Now, there are a number of different ways that can happen, and I think it's a good opportunity for us to move on to the next stage of this webinar. Now, I'm going to start by saying there are a lot of people who believe that fancy mathematical algorithms are of huge interest, are of huge importance in the world. And I'm not going to dispute that today, where consensus is concerned. What I want to do is look at more at the problems that we're solving with them than the minutiae of how they work. If that is something of great interest to you, I'm very happy to talk about it. It's quite easy to get hold of me. And equally, you will find there is a wealth of very, very in-depth material available on the internet. So how do blockchains use consensus? Now, first off, it's worth saying that different types of blockchains use consensus in different ways. But essentially, there are three things that we need to agree on between the different nodes of the network. So the first of those is to agree who gets to cut the next block. Now, this one specifically is a very different conversation in different kinds of blockchain and a very different kind of process. So we'll look at this one in a lot more detail. Secondly, we need to agree if transactions are valid and often what the result of those transactions is, so we can update our view of the world. So if we're making different decisions about that, that can make it very hard for the blockchain to run effectively. And thirdly, we need to agree what the underlying rules of the network are. Now, the degree to which this requires what we'd see as a consensus algorithm or a consensus process, rather than us simply having copies of the same rules, is very dependent on the type of blockchain. Now, this is much easier in general on private networks. If we agree who can join the network and what the rules of the network are, we have far fewer people to keep happy, and it's much less likely that anybody will act irrationally. And the proportion of people who will act irrationally, or when I say irrationally, I mean against our interests, that proportion is likely to be much lower because we are unlikely to have decent actors joining with what we're doing in an attempt to take over the network or subvert the truth and so on and so forth. Now, again, this comes down to who cuts the next block. If you think in a private blockchain, you're cutting the next block because you want to move some more data around. In a public blockchain, there is the incentivization of a payment for cutting that block. Therefore, it is in everybody's interest to want to cut that next block. Now, if we look at this practically, here's our private blockchain. We've got 4 participants here. Who gets to cut the next block? Now, 99 times in 100, everybody's going to agree Bob gets to cut the next block. You know, there are 4 of us here. We take it in turns. We know what the order is. We can all agree. Now, this is what's called a very simple version of Byzantine fault tolerance. You ask multiple people the same question. You expect to get the same answer. Now, we'll look at BFT a bit more in a minute. But it's worth looking at what happens when this goes wrong. So if one of these nodes goes wrong, or somebody replaces the software in it because they've had a bit of a funny morning, or otherwise seeks to change the network, it's very rarely because somebody is doing something evil because they're going to get caught. It tends to be because something has gone wrong. At that point, if 3 people say Bob and 1 says Liz, we can still agree it's Bob because we have a clear consensus majority view. And especially if that number is 11 and 1 rather than 3 and 1, you know, it's very easy to see what the right answer is. It's worth saying that with four people making a decision here, it's possible to get a deadlock. If 2 say Bob and 2 say Liz, that's going to cause you a problem. This is something that you've got to take into account when designing these networks. It's also worth saying that this idea that we can ignore a wrong answer by establishing what constitutes the overall consensus is what's called a practical fault-tolerant algorithm, as in it can, rather than simply identifying a fault, it can also resolve what the correct action is in order to move forward and move on to the next thing. Now, if we move to a public blockchain situation here, we've got a lot more participants. Now, here we've got about 30. In a real-world scenario, we could be looking at anything up to 100 or 200,000 nodes working in there, sometimes even greater numbers than that. Now, remembering that we have a financial incentive to want to cut the next block, I think we can all guess what's going to happen. If we ask everybody who gets to cut the next block, every single participant will answer me. Now, I think we can safely say that isn't going to work well. So what we need to do is we need to identify another method within those systems in order to decide who gets to cut the next block, and equally importantly, the rate at which we're going to cut blocks. Now, if you think about our private blockchain again, there is no reason why we cannot cut blocks as fast as the physical network will allow us. If we need to move that amount of data, everybody's very happy to do so. We're all gaining a benefit from doing so. If we're paying people to cut blocks, then if too many are cut, the value of the commodity which is attached to that will fall, removing the incentive to cut the blocks. Now, in a macroeconomic sense, it's been theorized that that will eventually move to people cutting at the right rate, but the practical implementation has not shown that to be the case. Therefore, algorithms are used that artificially induce a delay between cutting each block. Now, if we take the simplest example of Bitcoin, it is designed to cut one block approximately every 10 minutes. And remember that the financial incentive, even with the fall in the value of Bitcoin over the last year or so, the financial incentive for doing so is still in the region of about 15 grand. That is not a small incentive to want to cut a block. Therefore, what we do is we ask a hard mathematical problem that it is impossible to do anything but guess the answer to. Now, actually, what this means is that typically a question is asked where the hash of the previous block and what you want to cut in the next block is cut with a number such that the resulting hash, which is a one-way mathematical algorithm, starts with a given number of zeros. Now, obviously, the more zeros, the less the chance that any particular number input to that will return a number starting with 17 zeros. Now, if we bear in mind this is hexadecimal, that is going to mean that there's a 1 in 16 to the power of 17 chance of finding that number randomly. Actually, you can do slightly better than that. And it simply is a matter of brute forcing those numbers. This is what's referred to as mining. Now, if you imagine that there are chips out there now that can try anything up to 1 billion numbers a second against these on a single chip, and that means that these enormous numbers are being tried, and approximately once every 10 minutes, somebody will guess the right number. In this case, 31, because this is a very simple algorithm, and we'll get to cut a block. Now, I think we can all see the challenges in terms of the volume of electricity used in order to guess the correct answer here, and the negative consequences this can happen. And this is essentially hard to resolve. But you can see why consensus is much harder on these public networks. Now, there are two other things that I think are worth mentioning at this point, which are probably more in passing, and I wasn't completely sure how best to draw diagrams of these either, that I think we should mention. Now, the first of those is proof of authority, which is, you may have heard the expression proof of stake as well. That's kind of a proof of authority algorithm. So the idea of proof of authority is that we find some other way to decide who is authorized to cut the next block, either based on how many coins that person holds, or the amount of effort they put into the network, or just simply it's their turn, etc., etc. Now, there are various networks who have tried to do various things to solve this problem, and with varying degrees of success. Now, I think it's worth calling out the Stellar network in particular, because they basically run a process that they call supernodes, which are a group of 31 nodes who get to vote as to who cuts the next block based on essentially a round robin of people who hold their Lumen coins. Now, the process of deciding who those 31 nodes are is inherently challenging within a system like that. And because if somebody manages to take over just 16 nodes, then they effectively can control all future block cutting, because they get to decide who cuts each block. And if they answer themselves, then that is challenged. So the solution is, again, to distribute those nodes to trusted parties with a firm separation of control, so the quality of those decisions is still high. And this has been a challenge for them if it's an interesting subject to you, I thoroughly recommend Googling who has those nodes and looking at how that works. But this is a concept I want you to bear in mind as we talk about some of how gospel works in a moment. Now, the other thing that's worth talking about is something you may have heard the phrase block uncling, which is a strategy used by Ethereum amongst others, which effectively allows side chains to be cut back into the main network. And it's not really relevant to consensus, so I don't want to cover it in great detail here, but it's a way of dealing with the fact that sometimes two people will get the right answer to that mathematical problem we were talking about very close together, and before the agreed block has had the chance to move across the network and be accepted by everybody. Again, it's something that goes beyond what we're doing today. If that's something potentially of interest to you, maybe we can talk about that in a future webinar. Now, the other place where blockchains use consensus is around developing what the world state is. So our view of what happens when we've executed all the transactions that have been before. Now, if we think about this in terms of a simple ledger like you might see in bookkeeping, rather than something as complicated as what we're doing with blockchains, then essentially if we add down that column of transactions, we should get the same overall answer. Now, 3 plus 8, 11, 21, 32 plus 92 is 124, plus 18, 130, 42, 152, 160. So we've come to that. I've just been watching Philippa, who sat in the room with me, thank you, making the same calculation, came to the same result. So we've come to a consensus on what the answer to where we are now is. Now, if we gave those same transactions to, I don't know, Dave Revel, one of our excellent pre-sales engineers, he would come to the same conclusion. So by following those transactions again, we get to the same point, and we can have consensus about our understanding of the world as it is now. So if we receive another transaction, we all know that when we execute that, our view of the world will change in sync. So the result of adding 7 to the state of the world now is the same across everybody. And we can compare those results sometimes to make this work well. So the last of these topics that I want to cover in a kind of generic sense is the idea of simulation versus execution. Now, this is not something done by all blockchains. It is something that we rely on in Gospel. It's something that Hyperledger Fabric, for instance, uses as well. And it's the separation of working out what we're going to do and then actually doing it. Now, the advantage of this is we don't necessarily need to ask as many people what the result of a proposal is, what we say we want to do, before we can pass a much simpler set of results out to everybody. And I think there's an easy way of explaining this. So let's say from our office here in London, we decide we're going to drive to Nottingham after this meeting. And if there's 4 of us going, what we might do is ask all 4 of us to plan the route. Now, as we'll see here, 3 of us have made the very reasonable conclusion that we should drive up the M1. Most sensible way of getting to Nottingham, very boring road, but you know. And one person, I don't know who, somebody who's not very good at map reading, has decided we should drive up the A1M instead, which is a lot further and clearly suboptimal. Now, again, by a process of Byzantine fault tolerance, we can decide to eliminate that 4th result. Now, the way that we enforce this within a system like Gospel is that each node will return the result as it sees it, and it will sign it. Now, if we receive the same result from each of those nodes, each of the signatures will be valid against all of the results. So we can take one result, append all 4 signatures, or in this case 3 because we've eliminated one, and we have proof that those 4 nodes have come to the same conclusion cryptographically as to what should happen. And we can keep those signatures, and we can keep the proof that that was the result of executing it. That can then be put into a queue to be cut into a block and can be sent out to everyone. So if we look at this, our planning the route is the simulation of the transaction. We say this is the steps that we would take to change our state from being sat in the gospel offices in Fitzrovia to being sat in lovely sunny Nottingham. When we actually drive there, if this wants to move forward, then that is the execution of the transaction. So simulation is deciding how we're going to do it. Execution is actually doing it. If we look at that in a blockchain sense, then when we say, I would like to add £500 to my bank balance, if all the peers agree I can do that, the result that we actually execute is Reuben's bank balance was £3. It's now £503. And when we're making more complex requests, that can enormously reduce the amount of work that needs to be done overall. And it also means that we can get a view on whether something is likely to work before putting it into a block. And it eliminates a lot of the risk of failure. It brings practical Byzantine fault tolerance to the transaction. And it's just generally a better way of doing things. Now, where you're making very simple requests, where there's no chance of failure, no chance of disagreement in systems like Bitcoin, for instance, there's no need for this separation. With most of the things that people are doing with private blockchain, the necessity to separate these and the benefits it can bring is very strong. And I think increasingly the newer tier of systems tend to take this approach. So, the last of the things that I think we should cover today, before we take some questions, and please do keep questions coming in through the excellent facility at the bottom of your screen, is to look at how gospel is different to this. Now, fundamentally, obviously, we're not providing a blockchain system per se. We're providing a system that makes use of blockchain. But the way that we use it as a result is a little bit different to what other people are doing. And it has some interesting side effects as well that we should talk about. So first off, it's worth saying gospel can perform consensus on reads as well as writes. Now, this is something that you probably hear us talking about quite a lot. It's something on which we have a patent on the way, and it's something that we're very proud of. Now, why would we want to do this? Now, if you think a conventional blockchain system, I'm going to take Fabric here as an example because it's one, again, that many people listening are going to be familiar with. So with Fabric, each person will read from their own node. They know that they have a copy of the database. It's all relatively open data. So there is clarity about the data and there's opacity about how that data is used. So everybody talks to their own node. But when they want to write, when they want to make a change, they need the agreement of the network that that's an applicable change and that it can be made and it moves through that full consensus that we were talking about before. With gospel, our aim is to keep data very secure. So there is total transparency in how the data is used because we record all those reads as well as writes. We understand what people are doing with them. But equally, we do not want to give away what that data is without a reason. So by having consensus on reads as well as writes, by requiring somebody to read from all the nodes or an applicable number of nodes rather than simply their own, that also means that they can't decrypt that result without that consensus on reads. And that allows us to prevent somebody nobbling one node, stealing all the data out of it, whatever, and just reading the data out and completely bypassing all the controls we put in place. So with gospel, a transaction's result cannot be read until it has consensus. So nobody can take action unilaterally for reads as well as writes. And that gives us an immutable history of reads and writes. So we know nobody's done anything they're not allowed to. And we have a protection from security bypass through the consensus that we're talking about, because we know that nobody can do anything wrong. If you cannot gain consensus that you are allowed to read that data, if you can't get that agreement from the right number of companies taking part, that you're allowed to read it, that you're following the rules of the network, then you aren't going to get to decrypt it. And that means we know nobody can do anything wrong. So if nobody has done anything wrong and nobody can do anything wrong, that is the basis of trust. So we are leveraging consensus to build that layer of security, that unique layer of security. Now, I talked a little bit before about side effects. Now, if you think about what we were saying about Fabric before, everybody needs a node, right? If you don't have a node, you have nothing to read from. So that means if you look at things, and I'm going to talk about people tracking avocados on blockchains here. Now, I don't know whether this is a hypothetical scenario or something somebody's really doing. But if you think about it, if I'm an avocado farmer somewhere in California's Central Valley, the chances are I'm not going to be very well equipped to set up my own blockchain node. That's probably beyond my IT facilities. And as a result, this challenge that everybody taking part needs to have a node is very problematic for the practical adoption of a lot of these DLT-based solutions. Now, one of the effects of what we were talking about above, one of the side effects, and it's a very beneficial one, is that not everyone needs a node. Now, if you think, because we're all talking to multiple nodes, nobody is disadvantaged because they're not talking to their own node. Nobody is struck down a level or going to get the worst service because they don't have their own, because everybody is reliant on talking to multiple people. Therefore, whether I have a node or not, I have effectively the same access, and by the good graces of the network as a whole, allowing other people to cooperate with them, then I can ensure that everybody can feel secure, and my avocado farmer in the valley is just as well treated as the international distribution company who picks them up from him. Now, it is worth saying that for everybody to be secure, that means that we need to look at how we decide what is correct needs to work. Now, we need just enough people to ensure the decisions made are good, that they're reasonable, that they don't disadvantage anyone. So the rule of thumb is that we need one company that performs each type of function to have a node. Now, we should probably talk about this in a practical sense. So I have a series of companies here involved in the manufacture of toilet roll, because I thought this was a good example where I'm not going to offend any clients or potential clients. So we have companies who perform different tasks here. So for example, we have a couple of companies here who chop down trees, and a couple of companies who saw them up and turn them into paper. We have a company who makes plastic packaging. We have a couple of distributors, and we have an organization monitoring this process, because obviously we have these very strong audit logs to ensure that environmental standards have been made. So if we divide these into categories, we can see we have 5 separate groups of companies here, and we can see them as the logical groups, each one of which should have a node if they're part of the group that makes decisions. So if I pick 5 random companies in here, if we have these 5 have a node, then we will be able to make a decision where nobody feels discriminated against. So if we take Paperco here, which I actually got told after I made this presentation is apparently the name of a real company, but there we go, I did not know that. So if we take Paperco here, they will not feel disadvantaged by my paper mill having a node and them not having a node, for the simple reason that they know that they do not compete with Trees International, or Exciting Plastic Packaging, or the Corner Shop Supply Company, or indeed the Loo Roll Standards Boards. All those 4 votes, which constitute a majority of the network, have no interest in disadvantaging Paperco over my paper mill. Therefore, they can feel safe, even without a node, that their competitors are not in a position to disadvantage them. And where smaller companies want to be part of this process, and where the larger companies driving these adoptions don't want to disadvantage those small suppliers that prop up so much of the economy, this is an excellent reason, quite aside from all our security advantages, which are, of course, myriad, why gospel can be an excellent way of getting around this problem. Now, it's worth saying as well that quite often we'll have a situation where, for practical reasons, several companies in one area will have a node. Now, in this case, both distribution companies do have a node here, but what we will do is we will allocate only 1 vote from that category. Now, in practical terms, and I will say this, where we've done similar things in supply chain, we have seen where there are several companies in each layer have a node. What we can do is accept 1 vote from each area. Now, essentially, that means there's a mini consensus from each to get to the point of how that votes. What you do in practice is, in the simulation stage, you only ask one of those companies and you reduce everybody's load. So if we can get 2 companies in each of these areas, actually we can process twice as many transactions. Now, so there's one vote coming from the distribution companies. We might say that my paper mill still feels safe because it knows that corner shop supplies and or bulk retail distributors, again, will not disadvantage them. It's also worth saying that corner shop supplies knows that any transaction it hasn't taken part in endorsing, that's that simulation step, will not disadvantage it because it can see that the four companies in the other parts of the supply chain have no advantage in voting against them as a competitor. Now, there are some more complicated examples of that we've covered in some other times when I've talked about this topic, around things like where companies work in multiple levels of the supply chain and how to make that work. This is stuff that we've put a lot of effort into thinking about, and how consensus can be an algorithm of business rather than one purely of technology. And we do have some quite good written examples of how to work these things out. And I've got to say, our pre-sales team are genius at working this out and working with our clients to make the most efficient network in terms of the amount of technology that's used, the quality of the decision that's made, and the maximal level of security that is provided to our clients. Now, I think that brings us to a pretty good jumping off point. I'm going to take some questions in a second because I can see from my colleague's computer that quite a few have come in. But what I will say first is, first off, please do follow us on our social channels. Our website's Gospel Tech. You'll find us at Gospel Technology on YouTube and Gospel_Tech on most of the other networks. We also have another webinar next week, which I believe is with my able colleague, Trent Kalish-Smith, a very interesting man to listen to, about why PBFT is friendlier than it looks. So it's covering some of the things we've talked about today in a little bit more detail. And if you do have any questions or comments that come afterwards, either email into our general step.forward or come to me directly at reuben.thompson@gospel.tech. So now, I think that I did see a couple that we've already answered, potentially. But I have been asked, do all enterprise blockchains record reads and writes? Now, actually, no. So it is possible to record reads theoretically with a couple of the Hyperledger products. The only company, to my knowledge, that has a technique which can enforce the recording of reads is Gospel. All blockchains, by definition, do record writes. So it is very much a Gospel-specific thing that we are able to enforce consensus on reads, which allows us to force the recording of them. Without that, it is not possible to require the network to record that a read has occurred. So then we might be able to order a transaction containing that information, but it is not possible to mathematically prove that that is the case. The next question I have is asking, how do we manage to store all that data generated? Now, actually, we say all that data generated, but if we think about the volume of data we're talking about, first off, it's in 2019 terms, it's not a huge amount of data. So we tend to store information about people and things. And this again, is a point where I'll talk about Gospel because it's what I know, but I think what I'm saying is equally relevant to any other blockchain. It's information about people and things, whether that's money, whether that's things people have done, whether that's qualifications that they hold, whether it's items tracking through a supply chain. And there tend to be fairly finite numbers of those things. Therefore, the amount of data is huge to a human, but in terms of the volume of data that other computer systems store in this day and age, it's relatively limited. Now, even if we add in the number of reads going on, then it still is not approaching what you'd see in systems like Cassandra or HBase and so on. We're talking typically in the tens to hundreds of gigabytes level after a protracted period of using this, as opposed to in the hundreds of terabytes or the petabyte range. We have fired enormous amounts of data into various blockchains, including our own. And in general, the ability to hit read and write speeds is more of a challenge than the ability to store that data. Data storage is cheap. It's readily available from cloud providers. I mean, we, for example, work with all the major cloud providers, Google, Amazon, IBM, Azure, and so on and so forth. And really, you know, even where you've got multiple nodes and each is storing a copy copy of the data plus the metadata, and we do have compression as well, the volumes grow relatively slowly and are not prohibitive to store. It is worth saying that, eventually you may end up with a huge amount. You should think carefully about what you store on here, but it's not going to be huge compared to if you start data mining all your, internet traffic. It's quite easy to contain. I think as well, if you think about the kinds of data we're storing, it tends to have high value. So it's information about things that last a long time, have a lot of risk, have a lot of value. And as a result, the cost of storing a few extra kilobytes of information is minimal. Yes, we store a copy in each node, but if you ask a typical company, and I'm going to go back to an IBM study from about 4 or 5 years ago now, they estimated that companies were storing anything up to 21 copies of each piece of data. When you look at backups, when you look at multiple copies of databases, when you look at systems that have been offline, things that have accidentally been copied, mirroring on hard disks, etc., etc. With a fault-tolerant network like Gospel, or indeed many of these other blockchains, what you have is a situation where these multiple nodes and the separation of control between them means that actually backing up is of very little incremental value. So you typically will end up with far fewer copies of the data than the systems you're replacing. Now, I know that sounds like a bold claim, but it is borne out by what we've seen in the real world. People don't realize how much data they've got. And there are some excellent products out there for showing you. And I think many people would be genuinely surprised by how much is in there. Now, I'm going to answer one more question, and then I think we will probably close it down. I have been asked that what the transaction speeds within the network are. Now, people often ask the wrong questions with blockchain. I hear the question quite often, what's the maximum number of transactions per second? Well, that depends how complicated they are and many other factors, how quick your network is, same as with anything else, how quick your disks are, so on and so forth. Now, the right question to ask is the blockchain fast enough for the data you're storing? Now, there was a client I was talking to not very long ago who have a huge amount of data with very little turnover. And actually, it turned out that they were only making an average of 1 update a second. So fast enough for them is probably 10 times faster than they're going now. In other cases, I've seen people turning over a couple of 100. It depends on the complexity, but that should be achievable. Funnily enough, we were running speed tests earlier this afternoon and just generating data off some laptops. We were hitting a number that a conventional database would not have been upset by. So the question is it fast enough? Almost certainly for the kinds of high value data that people are storing within these systems, the answer is yes, it's more than fast enough. Where you won't often find that to be the case is with public networks like Ethereum, where there is a very limited amount of total data that can be stored in any period and people are competing for it. It is then very hard to get the capacity with a private network. That really should not be a challenge today. So I'd like to thank everybody for joining us today. As I say, if you have any future questions, do feel free to drop me a line, reuben.thompson@gospel.tech, or through to our team at step.forward@gospel.tech. Do follow us on Twitter. The company is gospel_tech, and I am libelous. I hope you will join us next week for Trent talking about PBFT. It'll be well worth your time, same same place. Hope to see you then.